Now, I think we finished 4.3. We're going to start 4.4 today. Do you guys have any questions up to this point? I should leave that up a little bit there. No questions? It's very exciting, all that good stuff. Okay.
Yep.
Oh, okay. Yeah, very exciting. All right. So Connor and Greta, up to this point, we have, well, I should basically say 4.4 isn't anything new. It's just the fact that we're going to extend everything that we've learned up to this point. So that's kind of the nice thing. Like, we're not really introducing, there's a couple new pieces of terminology, but it's basically like the next step from 4.3. So we're still talking about sine, sine, cosine, tangent, cotangent, secant, and cosecant. We're still talking about all those things, right? We're talking about what quadrant they're in and all that kind of thing. So we're taking what we know and we're expanding a little bit, but nothing new that we have to wrap our brains around immediately this morning. Okay, so back in the first couple sections about trigonometric functions and how they work, right? So back in 4.2 and 4.3, as I'm here, flipping my notes here, right? It's kind of all variations of the same thing is what we've been doing. So back in 4.2, if you remember, we talked about what the sine, cosine, tangent, and the inverse functions were. But we always talked about them when they were on a unit circle. Look at that nice circle there. So a unit circle basically just means that it has a radius of 1. So our radius is always 1. So it made it really easy when we were talking about trigonometric functions to tell what that point was. So for example, if I have this point here, and this is x, y, right? And then we extend this down. I will stay with purple. We extend this down and make it a right triangle, right? And this is our theta. Then, for example, the sine of theta, the SOHCAHTOA, right? Sine is opposite over the hypotenuse. Well, the opposite side is y high, right? And the hypotenuse is 1 because we had a unit circle, right? And so the hypotenuse, the radius is 1. So basically the sine of theta was the y component. Okay, so what we're going to talk about today is what happens if you still have a circle, okay, and the circle is still at the origin, all right, but instead of it being a unit circle, it has some other radius besides that. How do you figure out what the sine, cosine, and tangent are? So instead of 1, my magic eraser here, instead of 1, right, it has some radius. Right, so that means that when you find, for example, the sine of theta, instead of it being y over 1, because it was 1 before, the sine of theta is going to be y over the radius. Okay, and so before, back in 4.2, if you did the cosine of theta, it was x over 1, or just x. But in this case, we have some radius, so the cosine of theta is going to be x over the radius, and so forth. So that's what this box is right here. Basically just says that we're doing the same exact thing in 4.2, except we're adding in the fact that it's not a unit circle, it's a circle with some radius r. Okay, and so you can kind of see that picture here. There's the radius r, and there's some point x and y still on your unit circle. Okay, so and then you'll see this little formula, or this formula here: radius equals the square root of x squared plus y squared, and that's actually derived way stuck in algebra 2 somewhere. I think it was near third quarter, so somewhere in third quarter, we learned that the standard equation for a circle is x squared plus y squared equals radius squared. And so this equation here, the radius equals the square root of x squared plus y squared, basically comes from the standard equation of a circle. And I think I even popped this up last class, maybe online. Like if you wanted to graph a parabola, you'd do that. But if you wanted to graph a circle with a radius of 3, it would be x squared plus y squared equals basically 3 squared. Okay. And then if you zoom in on your circle, you'll see that this is a circle at 0 with a radius of, whoa, what happened? Oh, 3 cubed. I'm like, whoa, that's not right. Okay, 3 squared. There we go. All right, so there is our circle with a radius of 3. So 4.4 takes what we had in 4.2, but makes it a little more complicated because now we're talking about basically circles with a different radius, which means our hypotenuse has a different length than 1. Okay. Still the same idea though. So basically anywhere in your original your trig functions where you had a 1 before, now you have an r. Okay. Couple other things to note. So this is kind of like all the info at once, right? Couple other things to note. And again, we kind of want to flip between this and our big unit circle on the front. So I should have had that pulled up. Let's pull up a unit circle here. See, the unit circle will be your friend. This whole chapter. There we go. That'll work. Any unit circle will do, as long as it's labeled for me. Oh, that one's not very pretty though. Can we make it bigger? Now I'm being picky. Oh, there's a math wiki. How exciting is that? All right. So maybe not. Maybe I should find my unit circle that I liked that I printed out before. I can't find it. Math, unit, circle. I think it was math embedded or something. maybe. Oh man, I thought it would be super easy to find. Should just have it pulled up. All right, where are you at, unit circle? Oh, Matt. You guys, come on. That's how my day is going, huh? All right, this is gonna have to do. I can't find a good unit circle. All right, take 20. Let me actually just pull up my unit circle that I have. I should have it somewhere. Unit circle, where are you? I don't even think it's on my notes. All right, guys. All right, well, I totally distracted us looking for a unit circle, but let me just go back to my simple unit circle before. So what I'm actually going to try to talk about is the signs of each of our trig functions in each of the quadrants. Okay, so let me just kind of freehand this, and I don't even know if we need a unit circle. Okay, so if you have your unit circle, you can look at this and you will see that it's true. But if you are in quadrant 1 and you take the sine, the cosine, or the tangent, all of those are going to be positive, right? And that makes sense because your coordinate, this is a positive x and a positive y. So they're all going to be positive. So that kind of makes sense that since you're talking about the ratios of x's and y's to the radius, it's always going to be positive. Okay. When you move to quadrant 2 over here, right? If I really looked at this number, this is like you wouldn't write it like this, but this is like a negative x value and a positive y value, right? So this could be something like -3 and +2 to get to this x value, right? We really wouldn't write it as negative x, but the idea is that x is some negative value if you're in the second quadrant, right? So that means when you go to take the cosine, which is your x over your radius, and that x is a negative value, right? The cosine is negative. And then when you go to take the tangent, you have one of the terms is negative, so the tangent is negative. The sine, though, the sine is part of the y component, and the y is positive. So in quadrant 2, the sine is positive, the cosine and the tangent are negative. And that is reflected on your unit circle if you have, since you guys all have it on your front page, that's reflected on your unit circle. So if you look at all those values, the x values are negative, right? Negative square root of 3/2. And then the y value is positive. So that's how you come up with a positive sine and a negative cosine and tangent in quadrant 2. Okay. In quadrant 3, right? Quadrant 3 down here, you have a point. I want to switch colors. Okay. And so this is a negative x or negative y and a negative x, basically, right? So when you go to take the sine is going to have a negative. So the sine of any angle that's in quadrant 3 is going to be negative. And the cosine is going to be negative, but the tangent will be positive. So why is the tangent positive? Well, the tangent is positive because it's a ratio of y over x. So it's a negative over a negative, which becomes a positive. Okay, so in quadrant 3, your sine and cosine will be negative, but your tangent will be positive. And then here in quadrant 4, right, now we have a positive x and a negative y. So again, since the sine has to do with the y, it's going to be negative. Since the cosine has to do with the x, it's going to be positive. And since it's a mix of the x and y, the tangent will be negative down here in quadrant 4. So that's just kind of a guide to if you know your sines or cosines are going to end up negative or positive. And this is another depiction of that, right? This basically says in quadrant 1, x is greater than 0 and y is greater than 0. In quadrant 2, x is less than 0 and y is greater than 0. So that's what makes it, have these signs. In quadrant 3, both are negative, right? And in quadrant 4, x is positive and y is negative. So that's what that kind of depicts right there. Okay, Connor and Greta, you guys still here? Still
Yeah.
All right, cool. So again, it's kind of like taking what you know and building on it a little bit. Greta's here too. Awesome. Okay, last little piece of kind of upfront information about this is something called a reference angle. Okay, so reference angle is a little bit weird. It's just basically a terminology to understand. So this is what a reference angle is. Let theta be an angle in the standard position. So theta is just what we've always done, where you go all the way around to wherever you're at, okay? So, and these pictures here, this is a theta that's ends up in quadrant 2. This is a theta that ends up in quadrant 3. This is a theta that ends up in quadrant 4, okay? The reference angle is written like this. This is a reference angle. It gets a little apostrophe, if I can draw it with my pen. That theta gets a little apostrophe. It's called a reference angle, and it's always an acute angle. Okay, and the reference angle actually is the angle that is formed between your terminal side and the horizontal axis. So the terminology, I think, is harder than the visual. So the visual is, okay, that is my theta. The red is my theta for this one, right? This is my theta. The reference angle is the angle that is formed that connects back to my x-axis. That is the acute angle. Okay, so if this was 120 degrees, my theta is 120 degrees, my reference angle would be 60 degrees, right? It's an acute angle, and it's the angle that goes back to the horizontal axis, basically back to the x-axis. Okay, in this one with quadrant 3, my reference angle, you can see the theta with the little is the angle that is formed between my terminal point and back to the x-axis again. Okay, and then in the 4th quadrant, it's this angle here that's formed the last little piece. So you can see how you calculate each of those depending on where you're at. It's really just a visual thing, and a lot of times reference angles are used like in word problems. Hooray! Did you say word problems? Yeah, so a reference angle just basically takes you back to where you're at. Okay, so that is a lot of information. I am actually going to come back to doing some examples because I would really like to talk about 4.5 on the call today versus in class on Monday, because it's the graph of the sine and cosine functions. So I really just want to, I know it's a lot of talking, so take a breath. And we're going to start 4.5. And then if we don't even get back to examples in 4.4, a lot of them I think you can do anyway, because it's basically what we've done before. But again, I think it's easier to graphically see what's going on today. So, all right, so lots of examples there. All right, here we go. So this is 4.5. I don't know why I want to skip ahead. It's called the graph of the sine and the cosine functions. So we've talked about this, that this whole idea of the unit circle. So if I go back here to Desmos and I graph a unit circle, okay, and then I graph the sine of x and the cosine of x. Got all kinds of crazy graphs there. I zoom in a little bit. Okay, so this idea, I'll just leave the sign up there for first. This idea of the sine of x being a curve actually has to do with your unit circle. Okay, so if you do have your unit circle in front of you, okay, I'm going to leave this up on here and I'm going to look at my unit circle. So remember, on your unit circle, the sine of your theta, your x, right? The sine of your number is your y component. So when you're right here, when you're taking a theta of 0, your angle is 0, right? The sine of that theta is 0, which is why it's graphed right here. Okay. If you're looking at your unit circle, okay, and you want to know what the sine of 90 degrees is, or of pi over 2, okay, the sine of 90 degrees or pi over 2 is 1 because it's your y component. If you look at your graph here, pi over 2, the sine of pi over 2 or 90 degrees is 1. So that's how they match up on your unit circle. Okay? If I wanted to look at my unit circle and find the sine of pi or 180 degrees, right? That's going to be the sine of 180 degrees is my y component, which is 0. If I look at my sine graph, the sine of pi or 180 degrees is 0. Okay, and then so on, and it keeps going on. Hopefully that kind of makes sense as I explain it. I know it's a little bit hard. It's kind of like it's kind of cool to see how that unit circle basically kind of rolls out the sine curve, right? So then if you go all the way back, let me do this. If you go all the way back and I wanted to know what is the sine of 360 degrees or 2 pi radians, right? 360 degrees is when we go all the way around the unit circle and we come back here, right? The sine of 2 pi radians or 360 degrees is back to 0. And so if you look at the sine curve at 2 pi, it goes back to 0. And then it starts all over again, going around the unit circle to find those values. Okay, so, and then one point that you can actually really see visually on here is, I forget what those values are. I think it's 45 degrees, but I could be wrong. I think that's the sine of, no, that's not. I think it's maybe 30 degrees that you can see visually there. But, so that's how the sine works. Cosine works the same way. Okay, so if I graph the cosine curve, right, the cosine of 0 degrees or 0 radians is 1 because it's the x part, right? And that's why your cosine curve starts up here at 1. Okay. The, let's go over here. The cosine of 180 degrees or pi is -1. And here you can see on my cosine curve that the cosine of pi is -1. Right? And then this has the same property where if we go all the way back to 360 degrees, right, our cosine is 1, and the cosine of 360 degrees or 2 pi is 1. So it's kind of that there's this relationship back and forth between the unit circle and the sine and cosine curves. It's actually pretty cool, I think. Like, oh, it actually works, right? Okay, so couple things about the standard sine curve. You can see it on here. Okay. The sine curve has a period of 2 pi. So a period is basically where the curve repeats itself. I don't know if you learned this in physics or not, but like between 0 and 2 pi, we have one period, which means one wave of the sine curve. And then that basically repeats to 4 pi and to 6 pi and then off to the left. Okay, so the period is 2 pi, and that relates back to the fact that the unit circle, if you go around the unit circle, it's 360 degrees or 2 pi radians. So that's how they relate to each other. The period of a sine curve is the same as the rotation around a unit circle one time. Okay, you'll also notice that the range, okay, the values of y, if y equals the sine of x, if you take the sine of any angle, it's always going to be between -1 and +1. You can never take the sine of, pick any angle, sine of, 53 degrees. It's going to be some value that's in between -1 and 1, always. The sine of 1,000,000 degrees is still going to be some value between -1 and 1. Okay? All right. So then the cosine curve has the same properties, It's just shifted because we're on different parts of the unit circle, right? So the period of a cosine curve is also 2 pi. Okay, so it repeats every 2 pi. It just starts in a different position. And the range is also between -1 and 1. So whenever you take the cosine of any angle measurement, it's always between those two. Okay. And then here are just some graphs to kind of illustrate what I was showing about going around the unit circle, right? This is a sine curve. So here is basically when the angle theta equals 0, you start at 0, right? When your angle theta is 90 degrees or pi over 2, the sine is 1. When you take the sine of pi or 180 degrees, it's 0. The sine of 3 pi over 2 or 270 degrees, it's -1, and then back to a full rotation, and it's 2 pi over 0. So these words shouldn't be surprising. The spots at which we hit 0 are the intercepts. This is the maximum and minimum, right? And when you go through a full rotation of your sine curve, that's a full period. Pretty neat, huh? It's kind of fun to play with. Cool to look at, right? Okay. So then, but wait, there's more, right? So then we can actually, well, let's just talk about the standard sine curve. So basically what I'm saying is that if you take the sine of any number, right? And this, we're in radians, so pi times, I don't know, 500. Let's make it a really big number. 5,002. Oh, it's 0. All right, let's see, the sine, oh, that's because we're doing a multiple of 5. 0.5. 0.4. There we go. All right, so if you take the sine of some crazy number, right, it's always going to be between -1 and 1. Same with the cosine, always between -1 and 1. However, there are some times when you can modify your sine and cosine curves. Okay, so one of the ways that you can modify it is by changing the amplitude. Okay, so the amplitude is represented by the letter A, and it's basically you're multiplying the front end of a sine curve. Okay, so if I take the sine of x and then I do 3 times the sine of x, right? My amplitude, meaning the height of my sine curve, has increased from 1 to 3 by a multiple of 3. So by multiplying by 3 out front, I've changed the amplitude of my sine curve. So now if I took 3 times the sine of, pi over 4, then I could get a value that's bigger than -1 or 1, but that's because I'm multiplying by 3. So this is called your amplitude. It actually doesn't matter if you have a negative or a positive when it comes to amplitude. The negative obviously shifts your graph. It flips it over the x-axis, right? But the difference in the amplitude is the same. It goes from an amplitude of 1 to an amplitude of 3. Okay, or if you put in 0.5, right, you can decrease your amplitude by putting a number out front. Okay, so we know how we always talk about how your graphs shift. One of the ways that your graphs shift is by an amplitude. Okay, you can see that represents half the distance between the maximum and minimum values of the function is given by the amplitude. Basically, it's this number that is a multiplier. Okay, the other thing that you can do is you can change the period of a sine function. So again, the blue is my standard sine function. If inside my sine function, I multiply by 2, okay, now you'll notice that it's kind of hard to see on here, but the blue one is my regular sine function. So here it has a period of 2 pi, right? My green, I've multiplied by 2, so now I actually have a period of only pi. My period is cut in half by the fact that I multiplied by 2, right? The sine curve is basically going at a faster rate, right? If I multiply by 4, right? My sine curve has a period of, it goes through the rotations, basically this point here, right? Starts here and starts back over here, of pi divided by 2. So my period was 2 pi, and now it's pi divided by 2. Okay? And then on the flip side, what if I do 1/2 times x? Okay? Now, my original sine period is 2 pi. My new sine period is 4 pi. Right, so can you see how it's kind of like the shifting, right? Shifting of your graph. If you multiply outside of your sine or cosine function, it changes the amplitude, the up and the down. If you multiply inside, it changes the period, basically how fast your sine curve is repeating itself. Okay, and there's actually a mathematical formula that basically illustrates this. So if you have some number, an amplitude times the sine of bx, okay? So whatever this number is, we started off with 2x, right? Then the period is 2 pi divided by 2. So the period becomes just pi. So if you're multiplying by a bigger number, like if you're multiplying by 4, then your period becomes shorter. And if you're multiplying by a fraction, then your period becomes longer. Okay? So that is sine and cosine functions. And why I wanted to show you on the graph. While we're here, since we have it up, well, first of all, Greta and Connor, does that make sense? We'll do some examples with it, but kind of the idea of how we get the sine and cosine function, does that make sense? Greta says, yes, it do. Fantastic. Don't use that grammar on your English paper. But yes, fantastic. All right. So kind of cool. These show up in a lot of places, right? Yeah. Do not use, yes, it do. All right. So this is, again, jumping a little bit. This is 4.6. But what about, dun, 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 what about the tangent of x? What does that look like? What? All these other ones have these beautiful like curves, and here we go with tangent, and it's these crazy lines. Why is that? Why does tangent look so crazy? All right, so let's look at this period from 0 to 2 pi, right? This is one sine curve period. Okay, so right here, so we've talked about how the tangent, way back in our notes here, up here, the tangent is your y over your x, right? Or the tangent is also the sine of theta over the cosine of theta. All right, so let's stick with that one. I think that one's the best one. Oh, didn't mean to do that, but all right. So the tangent of theta equals the sine of theta over the cosine of theta, right? So if we keep that in the back of our mind and we go back to our graph, and I'm going to print screen this so I can write on it. Okay, so right here at 0, right? When theta or x equals 0, right? The sine is 0 and the cosine is 1, so the tangent equals 0. So when theta equals 0, the tangent 0, right? We're good with that. When theta equals over here, when theta equals pi, right? The sine, which is our blue one, the sine again is 0 and the cosine is 1. So the tangent is 0 again, right there. Okay, but then what happens when theta equals pi over 2 or 90 degrees? What happens right here? This is pi over 2 on, no, this is pi over 2, not like that. Pi over 2 on our graph, or 90 degrees. So what happens there is that the sine, right, is 1 and the cosine is 0. And can we ever divide by 0? No. So what happens is that our tangent at pi over 2 is undefined, and that's why we get this crazy tangent graph, because all of these are undefined and those are asymptotes of our graph. So basically you're taking the ratio of the sine curve to the cosine curve at every single point. Okay, and then at some point you can't do that ratio, so that's where you get an asymptote. All right, so I gave you basically a preview of the next 3 sections without doing any work behind them. I honestly think that you guys could probably tackle a lot of what is in 4.4. There's one, well, there's a couple of them where you just have to tell which quadrant it's in based off of the sign, the actual, not the sign function, but the sign of the value. I did want to show you one thing though, just to kind of make sure. So I know I threw a lot of information at you. We're going back to 5.4. We are going to go back here to when we were talking about, we're basically doing the sine, cosine, and tangent, but we're going to do it when we don't have a unit circle. Okay, so I just wanted to kind of show what that looked like. For example, in number 8, it says the point in these exercises, the point is on the terminal side of an angle in a standard position. Determine the exact values of the 6 trig functions of the angle. Okay, so number 8, we have basically a point that is at x equals -24, y equals 10. This graph is obviously not to scale. And this is where my point is at. Okay, and so I want to know what is theta? Okay, what is theta? And I want to know what is the sine of theta, cosine theta, tangent of theta, and all those things. Okay, so how are we going to do this? So I know that this is 24 units, right? It's to the negative direction. And I know that this is 10 units. What I don't know is, and I know that this is some theta, right? What I don't know is, what is my new radius, right, of this? And then I need to go from there and I need to figure out how to actually say what the sine, cosine, and tangent are. So I might have just confused you with a bunch of words, but basically this is my triangle here, right? And this right here is a reference angle. But I know all this information, but what I really need to know is how long is this side over here? Either of you guys have an idea how we could figure out how long that other side is? So this is a right triangle, and our good friend Pythagoras a long time ago taught us for all right triangles, a squared plus b squared equals c squared. Okay. What I'm eventually trying to do is to figure out what the sine, cosine, tangent, and all those are. But first, I need to know, I know that this is not on a unit circle. So I need to figure out what this side is. So I could do 10 squared plus 24 squared equals c squared. All right. And then if I add 10 squared plus 24 squared, I get 676 equals c squared. And that was nice of us. They made it work out. So c equals 26. Okay. So now what I need to do is I need to actually find out what my sine, cosine, and tangent are. Okay. And I'm going to do that by using my ratios, but then I have to use the knowledge that I'm in the negative. My x is in the negative. I'm in the second quadrant. Okay. So what that means is that if I wanted to find the sine of theta, okay, the sine of theta is equal to my y over my radius. So my y is 10 and my radius is 26. So the sine of theta would be 10 over 26, right? The cosine of theta is x over my radius. So my cosine of theta is negative 24 over 26, which can be simplified, right? And then my tangent of theta is going to be, tangent of theta is going to be 10 over negative 24. And again, all these can be simplified, but I'm kind of going fast here at the end. All right. So once I have all those, then I can find, the inverse operations of those. And then does this match up with what I know about what my trig function should be? So in the second quadrant, the sine should be positive, the cosine should be negative, and the tangent should be negative. So it does match up with what I have. So I just wanted to show you that. I know that I didn't get to do a lot of examples today, but I'd like you guys to go ahead and try try some of those out. Even if you get stuck in 4.4, you might be able to do 4.5 because I think that one's a little bit easier. So, yep, so that's it. So thanks for sticking with me with all those big, lots and lots of lecture today. So hopefully it all makes sense. And as you try it out, it all makes sense. Thanks for coming today, Connor and Greta. And I hope you guys have a good rest of the week, and I'll see you on Monday.